Today I'm going to talk about some miscellaneous components that are important and need to be talked about, but didn't really fit in anywhere else in the course. So I have a list of components here. We're going to talk about them, so let's get started. And the first one is a fuse. And let's take a look at the schematic symbol for a fuse. I'm used to seeing it drawn like this. Looks sort of like a switch, but it has a little squiggle in there. A lot of times the little circles are left out. There are other symbols for fuses, such as, I think this is one might be used in Europe. It has a line going straight through a component, looks like a European resistor with a line going through it. There might be another one too. Here's a diagram from Wikipedia of some symbols for fuses, and as you can see, this one's not on there, but there are the symbols. And a fuse is a device that will open a circuit if there is too much current. Notice I didn't say about protecting something. It does protect something, but people are confused about what a fuse actually protects. So let's take a look at what it does. For example, let's say we have, our power coming in off the mains, and it goes to some load here. So it's a motor, a light, some appliance, or whatever. Everything is working just fine. And let's say this is taking, maybe 1 amp, not a whole lot of current. And now let's say this fails in such a way that it becomes a short circuit. And now it's suddenly taking not 1 amp, but 50 amps. Now, should we put something in here to protect this from what just happened? Well, there's not much to protect. This has just failed. So what do we need to stop? So what's going to happen now is we're going to get 50 amps of current through a circuit that's rated at 15 to 20 amps. So what's going to happen? We're going to get heat, we might get smoke, melted wires, and possibly a fire. So this is a bad situation. So we need to do something to protect this system from what happens if this fails. We think about fuses being there to protect the circuit, but the circuit's already failed. So what we are protecting is the rest of the system. So what we're going to put in there, back in the old days, houses had fuses. I don't think you see this very often anymore, although you can buy the fuses. So maybe some old houses are still out there that have the fuses. They screw into a socket that looks just like a standard light bulb socket, but they are just a short circuit. I never actually dealt with them myself, but anyway, let's put the fuse here. And so that shorted out. Suddenly we have 50 amps. Let's say this was a 15 amp circuit. So what's going to happen? The extra current running through this fuse, I think fuses are normally rated to blow at about 1.5 times their rating. So a 15 amp fuse would blow at something like about 22 amps or something like that. But anyway, whatever it does, it's going to blow. That means it simply burns open. And now it stops the current from flowing, and we have protected the circuit. So that is how a fuse is used. Notice that we put the fuse in series with the load. So I'll put the fuse back here, put our load back over here. And we're expecting 1 amp in that load, 15 amp circuit, so there's a 15 amp fuse. And notice that the fuse is in series with the load, so that when the fuse blows, it stops the current to the entire circuit. Of course, if we stop the current here, we stop the current there, and that's the way a fuse normally works. Where we see fuses these days are in electronic equipment. Sometimes it's fused. Sometimes you might even find that probes to some kinds of testing equipment have fuses in them. Fuses are very common in cars. So there's going to be a fuse block somewhere. Here's one type of fuse that's used in older cars. These are fuses used in more modern cars. And so if something goes wrong and causes a fuse to blow, you need to go find your fuse box. My car actually has 2 of them, one under the dashboard and one under the hood. Quite a few fuses out there. And replace that fuse and hope that whatever caused the fuse to blow was a temporary situation. Usually it is, but sometimes you have nuisance blowing where I used to have a car where the brake light fuse blew frequently. Every few weeks it would blow and I'd have to crawl under there and replace it. And I'll talk about what I did to fix that more permanently later, because I'll be talking about circuit breakers in a couple of minutes. So cars tend to have fuses, electronic equipment tends to have fuses. You'll find them all over. This type of automotive fuse, as I showed here again, is quite common in that particular application. You can buy fuse holders of all sorts of types to put in your own equipment if you need to build something with a fuse. And then of course, cars have their fuse holders and other things have them built in. So that is what a fuse is. This is just elementary. There's a lot to know about fuses if you want to become an expert in them, but this is just the basic idea of what a fuse is and what a fuse does. It opens the circuit, stops the current from flowing, protecting the system from the circuit that failed, and once a fuse blows, it's done its job. You have to replace it once you fix the fault. Okay, so that leads us to the next item, which is a circuit breaker. And a circuit breaker is, there are a number of symbols for those too. Here's some from Wikipedia. I'm used to this particular symbol. Looks sort of like a fuse, but just has a little arc over it. And the difference between a fuse and a circuit breaker, the main idea is that a circuit breaker does the same job as a fuse, but once you fix the fault, you can reset the circuit breaker. Circuit breakers are very common in houses. If you've probably had that happen to you. A circuit breaker goes. Sometimes something has gone terribly wrong that has to be fixed, but as often as not, you try to run your microwave and your toaster on the same circuit at the same time. And if it's a 15 amp circuit, how about a microwave, a toaster, and a hairdryer at the same time? You're probably going to cause that circuit breaker to blow. And so you have to walk outside if you're unlucky. A lot of places have the breakers indoors. My experience is here in Southern California, the breakers tend to be outdoors. And so if it's not raining, you're lucky. But if it's raining, you have to go out and find that breaker, whether it's raining or not, and reset it. The breakers that we find in houses, if you go and look for the trip breaker, they look just like a switch. Here's a diagram, or here's a picture of one. And you go and look, and you might not be able to see which one is actually blown. Your typical house circuit breaker, when it blows, it becomes wiggly. So you might have to go and touch them. You might be able to see which one blew. You'll see all your breakers over on one side, and one's just not quite all the way over. That's probably the one that blew. And if you find that all of them are solid, but one wiggles a little bit, to reset your house fuse, you have to push it all the way off, push it off, and it goes click, and then force it back the other way, click, and it goes on. So that's your typical house circuit breaker. Circuit breakers work a number of different ways, some more than one way at once. So one thing that might trip a circuit breaker is heat. They have a bimetallic strip in there that will bend. Bimetallic strips, you have something like copper and tin bonded together. I'm probably not using the right metals. Might be iron and something, but they're bonded together, and since they expand at different rates, when it gets hot, it's going to curve, and that can break the circuit. And that'll be something that takes a little bit of time to actually break the circuit. But a lot of circuit breakers not only have a bimetallic strip, but they have some kind of a magnetic coil, such as basically a solenoid or a relay, so that if there is a sudden high current, that will break the circuit immediately. So sometimes a heat controlled circuit breaker, sometimes a magnetically controlled circuit breaker. A lot of them actually use both mechanisms. One for low overcurrents that can be tolerated for a time, and some for high overcurrents that can't be tolerated. Once again, when the circuit breaker goes, you need to push it all the way off and then push it all the way back on to reset it. Another place you find circuit breakers are aircraft. You don't find fuses in aircraft because when something goes wrong, you don't want to be fiddling around trying to find a fuse and replace it. You need to fix the fault and reset the breaker immediately. So here's a typical aircraft circuit breaker. It looks like a push button switch. When the circuit breaker pops, this pops out, and you can reset it by pushing it back in. Now, there have been some airplane crashes where pilots have been annoyed by alarms that happen frequently, such as takeoff configuration alarms that tend to happen while they're taxiing out. They get annoyed They got annoyed with this in the past and would actually deliberately pull that circuit breaker so you can actually manually break the circuit, and that would break the current to the warning system, and then they would eventually take off, not properly configured for takeoff, and there were a number of crashes that happened because of that. But you find this kind of circuit breaker in aircraft, and the circuit breaker panel is usually easily accessible, unlike the circuit breaker or the fuse box in a car, which takes a little hunting maybe to find it because it's not as critical. You can pull a car over to the side, a little difficult to do that in an airplane. So that's basically what a circuit breaker is. It's a fuse that can be reset. Oh yeah, and I mentioned I was going to say about my brakes that I had a nuisance blowing of the fuse every once in a while. Every week or so my brake fuse would blow. I don't know what was causing it. Got rid of the car many years ago. But what I eventually did was I got one of those aircraft circuit breakers and I soldered on the ends of a car fuse. So I smashed the fuse. It's made of glass with the two metal ends, soldered those to the aircraft circuit breaker and pushed that into the fuse block. And then if that circuit breaker went, I just had to reach under and give it a little push. And so maybe once a week or so, I had to reset that circuit breaker. But I don't know if they had those at that time. It's been a few years, but today you can actually get circuit breakers that go into your car fuse block that are, well, there are circuit breakers that have to be manually reset. Here's a picture of one here. And they also have circuit breakers that reset automatically. So the circuit breaker opens and give it some time and it will automatically close. And I think here's a diagram of one of those right here. So that is circuit breakers. So fuses have to be replaced. Circuit breakers can be reset. Okay, another type of circuit protection device is called a metal oxide varistor. Schematic symbol for this, here's an old schematic symbol, basically a circle with the letters MOV, and it sort of looks like a ceramic capacitor. And these are made of, like I said, they're called a metal oxide varistor. Originally they were developed as rectifiers, but it turns out that they have a much more useful property in that at low voltages they have a very high resistance, but at high voltages they have a low resistance. They're actually somewhat like a Zener diode. We'll talk about Zener diodes way down the road in solid state devices, but the idea of a Zener diode is that at a certain voltage it will start changing its resistance so that if you try to increase the current, it decreases its resistance so that the voltage stays the same. MOVs are similar, but they're used in a different situation. A Zener diode is used where you need to have a fairly precise voltage under varying currents. An MOV is used where you want to have the resistance drop very low when a high voltage hits it. So where would we use that? That would be for voltage spike suppression or surge suppression. And so an MOV, well, I like to describe it as sort of like an automatic toilet flusher. Let's take a look at what happens here. We have a pipe coming into the house, and that goes to the shower in the bathroom. Okay, there's your shower. And it also goes to your toilet. Okay, so somebody is taking a shower and somebody comes and flushes the toilet. Well, this pipe can only allow so much water to come into the house at a time. And so if you try to use the shower and the toilet at the same time, it probably can't deliver enough water to service both. So what's going to happen? Something's got to give, and what gives is pressure. So what happens is the pressure drops in the cold water line. And the person in the shower gets a bit of a surprise until the toilet stops filling and then the pressure is allowed to rise again. So suddenly the toilet becomes a low resistance. A lot of water flows in there that pulls the pressure down because this cannot deliver pressure fast enough, and the pressure drops. Well, an MOV works pretty much the same way. We have our power coming into the house, and there's a certain amount of resistance in that line coming in, so only so much current can come in before we have a dramatic voltage drop on this side. Remember, when we have current flowing through a resistor, we have a higher current, a higher voltage where the current enters the resistor, once again conventional current, higher voltage, more positive voltage where the current enters, lower voltage where it exits. Now this is alternating current, but the principle works the same whether the current is going one way or the other. We still get a lower voltage on this side than we do on that side if we try to take too much, well, no matter how much current's flowing through. If there's current flowing through resistance, we get a higher voltage where the current enters and a lower voltage where it exits. And if we have, oh, let's say here's a load over here doing its job, a little bit of current flowing through there. Now let's say we suddenly put another load that's a very low resistance in parallel. It tries to take a lot of current. Well, we try to take too much current through this resistance. It's going to cause that voltage difference to increase. This voltage is going to drop, and that's going to be our MOV. So if there's a sudden increase in voltage, this MOV is going to suddenly turn on and pull that voltage down. So it's going to absorb voltage surges or voltage spikes. Most MOVs I've seen, this may not be universal, but they are colored green. Might be different colors, but they're designed so that if they get over a certain temperature, that green coating turns brown to tell you that the MOV has probably been damaged by the voltage surge that it took in and needs to be replaced. So that's something, a lot of devices with MOVs have a little window so you can see if the MOV is green or brown, and might have to be replaced. You find MOVs in power strips or other devices that plug into the wall that are labeled as surge suppressors, but they're really not the best way to do it. You can get these surge suppressors for very low prices, but a good quality surge suppressor is going to have inductors and capacitors that can absorb the energy better than an MOV can. And so those are really not the best way to protect against power surges. If you want to protect, you're going to have to spend $30, $40 for a good surge suppressor rather than under $10 for one that just has an MOV. But that's what an MOV does. And by the way, an MOV, notice we put in parallel with the load. So the fuse, which protects against overcurrent, goes in series with the load, but the MOV, which protects against overvoltage, goes in parallel with the load. So that's what an MOV is. And before I forget, this is an old obsolete symbol. The new symbol for an MOV is a resistor with a line through it, looks like that. So either one, metal oxide varistor, and it's there to absorb over voltages or voltage spikes or power surges. Okay, the next thing we want to do is look at a number of devices here, thermoelectric devices. The first one we're going to look at is the thermistor. And the symbol for a thermistor looks an awful lot like the symbol for, or the modern symbol for the MOV, except there'll be a little letter T next to it. Older symbol, not much different, except it had a circle around it with a T in it, so either one of those could be a thermistor. Thermistor. So it's a resistor that is sensitive to temperature. Except all resistors are sensitive to temperature. Well, thermistors are resistors that are manufactured to have a certain coefficient of resistance based on temperature. So it's a known quantity and it's manufactured such to have a rather dramatic response to changes in temperature. There are two types of thermistors. We have those with a positive temperature coefficient, which means that as the temperature goes up, this is going to be temperature on the horizontal axis and resistance on the vertical. So as our temperature goes up, our resistance goes up. That is a positive temperature coefficient. And a thermistor with a positive temperature coefficient would have a plus T and a little degree symbol next to it. So that tells us it's a positive temperature coefficient, but they also make thermistors with negative temperature coefficients, which mean that as the temperature goes up, the resistance goes down. That would be symbolized with a minus T. So there's a negative temperature coefficient. So negative temperature coefficient, resistance goes down as temperature goes up. Now notice I drew these as curves because they're nonlinear, but if we combine the right thermistor with a negative temperature coefficient with another one with a positive coefficient, we can actually somewhat linearize this and get a response that's fairly straight. I'm probably drawing that straighter than it really would be, but you can get thermistors with either positive or negative temperature coefficients that are more linear, and they make those by combining both positive and negative temperature coefficient thermistors. And so, of course, these are used to check temperature. You have a little electronic thermometer, wherever it might be. They're going to use often thermistors to measure the ambient temperature. This is not like the ones that you just point, which have an infrared sensor, but these actually respond to temperature. So if you stick a thermometer in your mouth, it's got a thermistor in there. Pull the CPU off of a motherboard in a computer, you're going to see a little glob in there, a couple of leads off of it. That's a thermistor to measure the temperature of the CPU. So that's the purpose of a thermistor. So another type of device used to measure temperature is a thermocouple. And these are bimetallic devices. Once again, I'm going to make up the metals because I don't know off the top of my head what metals they use. But let's say it's copper and tin would work. I don't know if it's the best combination, but you bond those together and they act like a little battery. Even though there's no acid in there, when you bond two dissimilar metals together, they will release electrons at different rates from one side to the other. And so you get a little voltage in there, just a few millivolts. So I'll put a little MV here to show that your thermistor is going to develop a few millivolts, but it does develop a temperature, does develop a voltage, and that voltage changes with temperature. So temperature goes up, that voltage goes up. And so thermocouples are used to measure temperatures where it's too hot for a thermistor. So, for example, jet exhaust. They need temperature sensors in jet engines. Well, they're going to use thermocouples rather than thermistors because a thermistor will just burn up. Thermocouples can be made that can handle the temperatures. Another place where thermocouples are used are radioactive, RTG, radioactive thermoelectric generators. And most famous places those are used would be space probes. For example, the Pioneer and the Voyager space probes that are leaving the solar system. Well, even in the early parts of their missions, they were too far from the sun to get sufficient energy with solar panels, so they put radioactive thermoelectric generators in there, which means that they have a radioisotope such as plutonium that is decaying in a way that is releasing neutrons. Those neutrons are banging into other atoms. I think that's how it's working, and that produces heat. And in fact, here's a picture of a piece of plutonium used in an RTG. And so they surround that piece of radioactive material with a lot of thermocouples, and even though each one only develops a few millivolts, you put those in series, you can get enough voltage to run a spaceship. The Curiosity rover on Mars is running with a RTG because there are problems with using photocells on Mars, not the least of which Mars has frequent dust storms. I think they have them every other Earth year. And sometimes these dust storms cover the whole planet, but nevertheless, whether the dust storm covers the whole planet or just part of the planet, it tends to also cover the solar cells on the rovers that we send up there. One happy accident we found out is that very frequently there are dust devils on Mars that will clean off those solar cells. So some of the earliest probes we sent up there, we thought, okay, it got covered with dust, that's the end of that. Then a dust devil comes along, we got a new life to our probe. But they didn't want to worry about that with the Curiosity probe, so they used an RTG. Another place RTGs have been used is the Russian government has used them to power unmanned lighthouses in certain areas of their territorial seas. This led to an unfortunate incident where one was removed and dumped in a forest somewhere in Siberia. A couple of hunters came by and found this nice little warm thing out in the middle of the forest and said, hey, this is a nice place to camp, not knowing that they were being irradiated with nuclear radiation. And I understand that they died from radiation poisoning. So welcome to Russia. But anyway, that's what a thermocouple is, and thermocouples can be used to measure temperature or to develop voltages in a radioactive thermoelectric generator. Okay, another type of device we have is a Peltier device. Here's a picture of one. You may have encountered these if you have a device that you take camping, or just take in your car, where you can plug it into the cigarette lighter plug, and you can flip a switch and either gets hot inside or cold inside. It's a heater or a cooler. And you might have, I think this is kind of a little fun thing, you might find a little thing that you can put a can of soda in and plug it into your computer and keep your can of soda cold. That also uses a Peltier device. And they're also used under CPUs sometimes to help transfer heat from the CPU to the heatsink. So what a Peltier device is, it's a device that if you run a voltage to it, it will get hot on one side and cold on the other. It transfers heat from one side to the other. So one side gets cold as it takes heat away, the other side gets hot as that's where the heat goes. But heat sinks and fans on both sides, and you can drive energy into the cold side and then drive it off of the hot side, and you can get a small space, maybe as much as 40 degrees colder than the air around it. Of course, if that's in a hot car that's sitting at 120 degrees, it's still going to be 80 degrees inside, but you can also stack them together to increase that temperature differential. So a Peltier device, they used to be pretty expensive. I built a little 6-pack cooler once using a Peltier device. That's why I learned that you had to have heat sinks. If you don't have heat sinks and fans, they really don't work that well. So you sandwich the Peltier device between two heat sinks and run fans on those, and you can get a good temperature gradient. And it'll actually, the one I bought for it's $20 for the Peltier device, was able to cool a space the size of a 6-pack. So when I was a truck driver at one time, no, it was not a 6-pack of beer, because that would have been highly frowned upon, but it kept my soda cold. And you can buy all sorts of Peltier coolers these days, once again, used in coolers and sometimes used in CPUs or computers to get the temperature from the CPU, the energy from the CPU to the heatsink. Could we make solid-state air conditioners with these? That's a nice thought, but I don't think they're efficient enough to even think about that. But interesting device, the Peltier device. Okay, so that was thermoelectric devices. Now let's look at some photoelectric devices. First thing we're going to look at is a photovoltaic. These are something becoming fairly common because the sun falls on them and they produce voltage. I think one cell produces about half a volt. You can put these in series and get more voltage, make more area and get more current. And of course, you may even have these on your house as we speak, or other devices. I have a calculator that, well, here it is. Little calculator with a solar cell right there. Never have to put a battery in this. As long as there's a little bit of light, it's enough to run this little calculator. And once again, you have big ones on houses, or you can have whole solar farms using photovoltaics. These are usually made of silicon. They're basically a silicon diode. Light falls on them and they produce voltage. Another device is a photoresistor. Here's a picture of a cadmium sulfide photoresistor, and what these do is, as light falls on them, they have less and less resistance. So they have a high resistance in the dark and a lower resistance as more and more light falls on them. I made a video doing a review on some flashlights I bought at Amazon that did not live up to their power output as far as I can tell. And I simply used a cadmium sulfide photocell that was on this old Radio Shack 130-in-1 little project kit, and I used that to compare the light output of these flashlights to some other ones. And I don't know if the other ones were accurate at all, but they did not live up to the 1500 lumens that were advertised. I'm pretty sure about that. But anyway, photoresistor, as the light on it increases, the resistance goes down. Okay, there's another device called a photodiode. I'm going to talk about those more in the solid-state devices, but it's basically like any other diode. This is the symbol for a diode. Photodiode was going to have a little lightning bolt pointing to it, which means it's light sensitive. And if we bias this such that the cathode is positive and the anode is negative, it's not going to conduct current that way, but as light falls on it, it does start to conduct. So it works a lot like a photoresistor, except it only works one direction. If we bias it the other way, positive to the anode, negative to the cathode, it's going to conduct like any other diode. But we reverse that, negative to the anode, positive to the cathode. Like any other diode, it's not going to conduct, but if light falls on it, it conducts. The more light, the more it conducts. Very closely related to the photodiode is the phototransistor. This is a bipolar junction transistor that's actually also a phototransistor. I'll put a little lightning bolt pointing to it. Sometimes I might put a little lambda, or I mean a little gamma next to it, either one or the other, to show that that is photosensitive. Now, I'll talk about transistors in the solid-state devices way down the road, but basically we set this up with a positive voltage here, ground here, and a slight positive voltage there, and the more current we have go from the base to the emitter, the more current we have go from the collector to the emitter. And that's what our transistor does. Increase a little tiny current here, big current here. Make this bigger, this gets even bigger. That's how it amplifies. It doesn't magically get energy. We have to have a battery driving it, but it acts like a current-controlled switch. And the more current, well, more like a current-controlled variable resistor, the more current goes from the base to the emitter, the more current goes from the collector to the emitter. But a phototransistor, which may or may not have this wire going to the base, is also light sensitive. So the more light that strikes it, also the more current from the collector to the emitter. So photodiode and a phototransistor work very similarly. Photodiode is much more responsive. It responds faster than a phototransistor, but the phototransistor will give us a bigger ratio of light to current. So faster, more amplification between the photodiode and the phototransistor. Okay, so that's photoelectric devices. Now let's look at some electromagnetic devices. I've already talked about solenoids, which use coils of wire to create magnetic fields, which will then attract an armature, causing either linear or sometimes circular motion. And of course, motors are electromagnetic, but what I'm talking about are electromagnetic devices that react to magnetic fields in a different way. And particularly what I mean is the Hall effect. So if we have a conductor and there are some electrons moving through it, of course the electrons are going to drift evenly spaced through the conductor. But if there's a magnetic field, I'll just draw that as parallel lines. If there's a magnetic field and the electrons are moving, they're going to be either repelled or attracted to that magnetic field. So let's say that those electrons, let's go ahead and erase the magnetic field here just for clarity. And so here's our conductor, and there's electrons moving through there, and they pass through a magnetic field. They're going to be either attracted or repelled by that magnetic field where they see it. So there's a magnetic field right in this area. So what that's going to do is it bunches the electrons on one side. And so what do we get? More electrons here, less electrons there. So there is a potential difference there. We get a negative charge on this side and a positive charge on that side, or should I say a negative potential and a positive potential. So there is a slight voltage across a conductor that has a magnetic field around it and moving electrons. And once again, that's called the Hall effect. And there are solid-state devices that take advantage of this called Hall effect sensors. They look pretty much like a small signal transistor, but you look at the spec sheet to see exactly how to use them, but they can sense magnetic fields. So that's just a solid-state device, the no moving parts, that can sense magnetic fields. Okay, last family of devices we're going to talk about are crystals. And we're going to talk about a property called piezoelectricity. And a crystal, typically they're made of quartz, but they can be made of other devices. I know of a particular brand of crystal microphone that was made from something called a Rochelle salt. You can look that up to see what a Rochelle salt is, but they use those to make a particular microphone. It was known as the Astatic D104, very popular in ham radio and CB radio at one time. Yeah, there's a picture of one right there. So anyway, a crystal has an interesting property. If we take a slab of crystal, and typically they're made from quartz, so they'll take some quartz and cut it and grind it into precise slabs. And if you distort that crystal, it will develop an electric field across it. And consequently, if you put an electric field around a crystal, it will distort. So it works both ways. And where you see this used is one is crystal microphones. I'm going to talk about that first because it uses the distortion factor, and that if you talk on a crystal microphone, it makes it vibrate, and that causes it to develop alternating voltage of positive and negative voltages, and that can be channeled off with wires. So there would be a couple of plates on there, and with wires on them, looks sort of like a capacitor. In fact, it does have capacitance because we have two conductors separated by an insulator. But in the case of a crystal, the piezoelectric effect causes it to produce alternating current as it vibrates, and we can take that alternating current and amplify it. We'll talk about that kind of thing in the analog circuits at another time. But also consequently, if we send an alternating current to it, it'll cause it to distort back and forth, so it'll also act like a speaker. So we have a something that acts both like a microphone and a speaker at the same time. And sometimes some very sensitive earphones are made with crystals. And they were popular with what are called crystal radios, which has nothing to do with the crystal for the earphone, but they could pick up radio signals without amplification. Because these crystal earphones are very sensitive, you can hear the radio signals without any amplification. And there are also high quality crystal microphones used in sound production. Not as common as dynamic microphones or ribbon microphones, but they do exist. Obviously, they have a very high impedance because there's no electrical connection between the two plates. But that's one property of piezoelectricity. One, you distort it, you get a voltage. If you put a voltage across it, it distorts the crystal. Another way this is exploited is in radio circuits, not necessarily radio circuits, but in oscillators that are often used in radios. We have a crystal. Here's a picture of the inside of one here. You can see the crystal with the plates on it. And what that does is if you put alternating current across that crystal, so it'll draw it again here with the two plates. If we put some alternating current across there, that crystal wants to vibrate at a very precise frequency. And so if we run this to an oscillator, I'm just going to show that as a simple symbol. I'm going to show it kind of feeding back to itself here. But the idea is that if we build an oscillator that wants to oscillate at a particular range of frequencies, this crystal will cause it to oscillate at a very precise frequency, especially if we keep this at a precise temperature. And in fact, the crystals that are used to control commercial radio and television transmitters have little ovens to keep them at just a precise temperature so that they are very, very stable and operate the master oscillator that runs the station so that it doesn't drift off frequency. But of course, other devices, radio devices, may use them too. Anything from ham radio handy talkies, citizens band radio, family service radios, anything that has a radio in it will have crystals controlling the frequency if you need precision control. And modern radios use digital electronics to take whatever frequency comes from the crystal and to multiply or divide those frequencies to get almost any frequency you want. Talk about that another day in communication circuits. They're also used in just regular receivers, like if you have a radio receiver in your car, there is a oscillator in there that controls what frequency it picks up. Once again, that's something to talk about in the communication circuits, but that oscillator in there will these days be crystal controlled because your car radio is going to be computer controlled, and it can use circuits to develop whatever frequency it needs from that master crystal oscillator. And so we see those all over the place. Even the tiniest little FM radios will tend to have a crystal oscillator in there controlling them. And of course, computers and other digital devices, it's very easy to make an oscillator with a crystal. They're so cheap that it's better to make them that way than any other way. So we have a digital inverter, put a crystal across it. I'm oversimplifying, of course, but we can get that to oscillate at a particular frequency. How about a digital watch? I think this will oscillate at 32,768 hertz, which is divided down through dividers. That is a power of 2, so it's very easy to divide it down to 1 second. So 32,768 vibrations per second goes through some what are called divider circuits. We'll talk about those in digital electronics to get us down to 1 hertz to control our clock. Computers use the same kind of circuit just to run the computer, because there has to be an oscillator that makes the computer, every time it oscillates, it makes the computer go through one step of whatever it's doing. So digital circuits, especially those with controllers, microprocessors, or whatever are in there, have to have oscillators that make it do its stuff on each pulse. And those will be crystal oscillators because they're cheap and quick to make. So that's two places we see crystals using the piezoelectric effect. A third way is just to make a spark. Do you have a cigarette lighter where you press it down, it goes click, and you get a spark and it lights the cigarette lighter, or any other type of device, a torch or whatever? Sometimes a camping stove, to light the stove, you have to press a button and you can actually feel it cock a hammer, and the hammer hits a crystal and it creates enough voltage to actually create a spark. Here's a unit that does that. Press on the button here with a device and it cocks a hammer, and at a certain point it releases it. That hits a crystal and creates thousands of volts, enough to make a little spark to light a cigarette lighter or a camp stove or something else. So those are the places we see crystals. So those are some components that need to be talked about, but just didn't fit anywhere else in the course. And I'm sure some of you are saying, hey, you forgot about? Well, if I did, go ahead and talk about that in the comments, and I'll get a few of those together and I'll make a supplemental video about those other components that you request. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.